called convolutional neural nets. Okay, so last week we introduced what a neural network actually was, and
Sorry, just a clarification. On the syllabus website, it says our midterm HD to be one-sided, but your post says two-sided.
So I'll edit the syllabus. You can have two sides. Although, as I said on the post itself, use the aid sheet really as a tool to study for the midterm. I think you'll find that you may not have a lot of time on the actual midterm itself to make a lot of use of it. Okay, so what we're going to do today is learn weights in a multi-layer neural network using gradient descent. And so this is the exact recipe we followed in the past for linear logistic regression. And now we want to do it for this directed acyclic graph that's a neural network. So what's in the weights? What are we actually learning? Well, last week we talked about the idea that a neural network is nothing more than a compositional set of functions. Each one is a linear operation followed by a nonlinearity. So the weight space is the set of weights for each unit in every layer of the network. Each hidden neuron is computed as a result of some linear operation and nonlinearity. We're going to take all of those weights and stack them together across all the layers, and that's going to be the weight space for this neural network. Then we're going to define this loss function. So as I mentioned last week, what the loss function is going to be is going to depend on the task you care about solving. If you want to do regression, you could use mean squared loss. If you want to do classification, binary cross entropy. And if you want to do multi-class classification, you'd use the softmax cross entropy loss. And our goal really in the first part of this class is to think about computing DLDW. Because DLDW is the thing we need in order to actually learn. Because to do gradient descent on the weights, we need to compute the gradients. And so this is a really simple example of a two-layer neural network that's sort of been blown up to scale, and I've put down on each edge the actual weight corresponding to what needs to get learned. So there are two inputs. The input is two-dimensional, x1 and x2. And there are two outputs, y1 and y2. There's one hidden layer, and the hidden layer has two neurons, h1 and h2. And these are the nodes in the graph. So all of these ones are really just bias units for the linear operations we care about. And to compute the hidden neuron h1, we're going to take this weight. We're going to multiply it by the number 1 to represent the bias. We're going to add to it the product of x1 times w111. And we're going to repeat the same thing to multiply x2 with w211. So h1 is going to be 1 times w01 plus x1 times w111 plus x2 times w211. And that's how we get h1. And we would do a similar thing in order to get, so that's what we would do to get h1, and then we would apply this nonlinearity and apply a similar process to get the outputs, where the new inputs to compute the outputs would be h1 and h2. So I'll pause here for a second to see if folks have any questions on how to read this graph. Because we're going to be looking at a lot of graphs like this, so any questions or any confusions, now's a great time to ask. Yeah?
For the connection from H2 to Y1, shouldn't it be W?
Yeah, there should be a W21. Yeah, that's a mistake. Okay. So this is, again, recap from last time, except written out with the computation in the form of this graph. So as you go from left to right, what you are doing, given any input x1, x2, is computing the hidden representations in the graph and eventually computing the output. So each edge denotes some form of computation, and each node denotes either an input, a parameter in the case of the bias, or an intermediate computation of this neural network, which are the hidden units, or an output. And so, as we said before, a neural network computes a composition of functions. So we're going to compute first Z1, which is the pre-activation output that is obtained by doing the linear operation on the inputs in order to get Z1. And Z1 is passed through a sigmoid nonlinearity in order to get the value of H1. And so these two lines here correspond to the computation of taking these three things and computing H1. Similarly, you can ask the same thing for computing H2, which would involve taking these three inputs and computing H2. And so once you have H1 and H2, you're now ready to compute Z1 and Y1 correspondingly. So you should all be really familiar with this idea of linear operators followed by nonlinearity, and this is just writing it out one equation at a time for every single node that's in the neural network. So any questions that, in terms of clarity of what's going on in terms of the computations here? Yeah. Yeah.
Typically when we're doing like just one thing, we add one bias term to the entire like computation.
Yeah.
But in this we seem to be adding bias like per node kind of.
Yeah.
So is that how like a difference between just what we learned earlier in neural networks, like you can add more biases?
Well, each layer has a bias. So if you think about linear and logistic regression, the reason we just added the bias as a vector of all ones to the input is because there was one bias that we cared about learning. In a neural network, each hidden unit has its, in some sense, its own bias. And so here H1 has this weight as a bias, H2 has this weight as a bias, which is why we sort of disentangle it and split it out. The other reason is that you can't just add a single vector of ones to the input and use it to represent all the biases in all the subsequent layers. Because remember, this is a nonlinear operation. And if you were to add the bias to the first inputs itself, it would not be an equivalent operation relative to considering the biases in the second layer. And so we want to make it clear that since we're moving to nonlinear models, we do have biases on a per layer basis. So you could do the trick of padding the inputs at the first layer, and that would allow you to remove these two biases, but it would not allow you to remove any of the subsequent biases. Yeah?
How do we read the superscripts and subscripts for the weight?
So the superscripts here denote the layer. So this is layer 1 and layer 2. And the subscripts, in theory, although someone just pointed out this bug, this should be 2, 1, should denote the input. So this is an edge from 1 to 2. So this is an edge in the first layer from node 1 to node 2. So this is input 1 to hidden unit 2. Thank you. That's a good question. Okay. So given that neural network, you can go all the way to compute the output. And once you've computed the output, you can also compute the loss function. So just for simplicity, we've sort of assumed that this neural network is actually simultaneously solving 2 regression problems, so it has 2 outputs. And for each of the regression problems, you're going to train it with the mean squared error loss function, which is represented via this equation at the bottom. And so what we'll do right now is take a look at a model that we've looked at but discounted in the past. And the reason we'll do that is mostly because it's instructive to look at the logistic least squares loss function. So the logistic least squares model and loss function says that you're going to first apply a linear operator to your input. Then you're going to apply the sigmoid nonlinearity, and you're going to train using the least squares loss. And remember, this is not how we actually do binary classification, but the reason we're going to study this in the context of learning backpropagation is because it's a very simple model, and the gradients are nice and easy to look at, which makes it easier to understand what backprop is doing. So in this model, we again have our nodes, the inputs and the parameters of the model, and we also have intermediate computation. So the Z is an intermediate computation, Y is an intermediate computation, T is a target, and that's going to be an input into this graph, and L, the scalar, is the loss function. So in this particular graph, it kind of looks like the one that we had before, but we've gotten two new additions to it. The first one is the actual target, and the second one is the loss function. And so the reason we're writing this out in a graphical form, as you'll see in a few slides, is because it gives us an easy and convenient way to think about backpropagation. Questions? Okay. So as I mentioned to you before, the nodes each represent inputs as well as computed quantities, and each edge represents which node are computed directly as a function of which other nodes. So if you were looking at a single node in the middle of the graph, to understand how you obtain that node, you only need to know the values of everything that is immediately to the left of it, all of its parents. So given the values of X, B, and W, you have all the information you need to compute Z. Given the value of Z, you have everything you need in order to compute Y. And so on until you get to the loss function. And so what this graph, this computational graph is really doing is that it's breaking up the process of evaluating the model and comparing the prediction of the model to a target as a topological ranking of nodes in a graph. Because as you go from left to right, if you follow through and plug in values for each of these nodes, you'll see that you go from an input to the evaluation of the loss function for that input itself. Any questions about reading this graph or what any of the nodes or edges mean? Okay. So now that we know what a computational flow graph is, we're going to start thinking about derivatives and how we can use the graph in order to start estimating the derivatives we care about. So the first rule we'll need to make use of here is the univariate chain rule. So let Z is equal to f of y and y is equal to g of x be some set of univariate functions. And so we can compactly write down Z as a composition of f of g of x. So all this is saying is that instead of first computing y and then computing z, you can write this z down compactly. But this representation means if you were to take derivatives of f with respect to x, you'd have to apply the univariate chain rule. So to take dz by dx, which is how does z change as a function of input x, we need to first evaluate the gradient of z with respect to y, the gradient with respect to the intermediate computation, and then multiply that by the gradient of y with respect to x. So this is just, Calculus 101. I've said nothing interesting other than the chain rule here. And so we can ask for the logistic least squares model and loss function, how do we actually evaluate the gradients with respect to the weights and the biases of the model? And so you did this by hand in the previous lectures, and you've played around with it in the context of your homework assignments now. And so you would effectively use tools from calculus that you've used in the past. So to do this, you would first write down what the loss function was, and here it's written down as a function of the inputs that we care to differentiate with respect to, both w and b. And then this is just a function of the weights. So we want to take a gradient of this function with respect to the weights. So we'll first do this process for dl dw. So we'll move the derivative operator inside the brackets and then apply it to the squared operator. So we would get 2 and 2 cancel out, and we'd get the input times the derivative of whatever was inside this, which gives us this particular line. And now to evaluate this derivative with respect to w, we only care about the first term. And so we would take the derivative of the sigmoid operation and apply the chain rule again to multiply that with the derivative of the input to the sigmoid with respect to w. And finally, that gives us the answer that we need, which is this line at the very bottom. And this should look very familiar to all of you by now, because this is just y minus t times the derivative of the sigmoid with respect to y, sigmoid of z times x, which is the gradient that you've all seen many, many times in the past. But now, it's not just w we care about getting gradients with respect to, it's also b, the bias. So what we're going to do is go back and evaluate gradients with respect to b. And we'll follow many, many of the same steps until we get to this last line here, where the only difference is that d of this quantity with respect to b is a 1 rather than an x. So what are some of the disadvantages of just doing this manually via calculus? Yeah. It's easy to make a mistake because for each and every weight in the model, you have to rederive these rules, and so one mistake would propagate through all these derivatives. That's a good point. Any other disadvantage you can think of? Yeah.
It gets exponentially harder the number of layers we add to our neural network.
So it gets exponentially harder. Why is that hardness complicated? Like, what about that makes it complicated? Like, in some sense, we have to pay that price to get gradients. But what about this setup makes you think that that gets harder? You're kind of on the right track.
I guess it's just like if we want a computer to calculate for us, they're not good at calculating, like evaluating complicated expressions as good as they are just brute forcing.
Right. So maybe it's difficult to tell the computer all the rules that you might want it to do in order to come up with these derivations by hand. But this notion of the fact that it gets computationally harder as you get deeper is sort of underlying an interesting idea, which is that if you look at just dl by dw and dl by db, you'll notice that we're doing a lot of the same operations. For most of these derivatives that we did by hand in these two columns, we sat and computed the exact same numbers for a lot of it until we reached the very last line. And so we can first, this is just a repetition of the computation of dl by dw, now written out in univariate chain rule form. And you'll notice here that in order to compute it, we needed 3 quantities: dl by dy, dy by dz, and dz by dw. When we do it with respect to b, we need 3 quantities again: dl by dy, dy by dz, and dz by db. So really, if we were to put these two side by side and compare them, there's only 2 things that change. It's this and this that change when calculating the derivative with respect to the inputs. And what that means is that if we can come up with a clever way for us to compute these 2 quantities just once, then we can share that computation when we compute the derivatives with respect to w and with respect to b. So I'm going to pause here and see if folks have any questions about the idea that when we're calculating derivatives in the context of logistic least squares, there is shared computation that we can leverage in order to compute the derivatives with respect to each of the weights. Okay. So if you're comfortable with that idea, then intuitively what we want to be able to do is come up with a structured way of computing gradients. And this goes back to the point your colleague made, which is maybe it's difficult to teach a computer to manipulate symbols. But if we give a computer a basic recipe, can it use that recipe to calculate gradients with respect to any function and any input? And that's really what the backpropagation algorithm attempts to achieve. And so in order to see how to algorithmatize this idea of sharing computation of the derivatives, we're going to need a little bit of notation. So the notation that we'll introduce here is what's called the error signal notation. So whenever you see this y bar, what you're going to do is you're going to substitute it by dl by dy. So I'm going to define y bar for any y as dl by dy, where L is the loss function that we care about taking gradients with respect to. Now, these are just mathematical values that our program is going to compute. And what we're going to do is take a look at the process of applying this chain rule and see what it looks like when we use error signal notation. As before, we're working with the logistic least squares model. So we have z is equal to wx plus b, y is equal to sigmoid of z, and L is equal to the squared loss. And to compute the gradients with respect to the input, we're going to go backwards in the flow of operations that we had. We're first going to compute the gradient of the loss with respect to y. So that's dl dy, which as we said before was y bar. And you can verify that dl dy is just y minus t. So that's just the difference. So that's what happens when you take the derivative of y with respect to derivative of L with respect to y is equal to 2 by 2 times y minus t. So that gives us the first equation. The second equation, dl dz, well, to compute dl dz, we know that we can apply the chain rule. We would first compute dl dy, and then we would compute dy dz. But dl dy is the quantity we just computed in the previous step. This is just y bar. So we can write dl dz as y bar times dz dy. And that's exactly what we've gotten in the second equation here. Finally, we're sort of ready to calculate dl dw. And we're going to calculate this as dl dy times dy dz times dz dw. But again, we're going to notice that this quantity here is exactly what we computed in the previous step, because this quantity here is z bar. And so by replacing z bar with the quantity that we needed to compute, we can sort of share and pre-compute what z bar is and reuse it when we compute dl dw and dl db. So any questions about the error signal notation, how the error signal notation can be used to represent the univariate chain rule, and why this representation enables us to compactly write down gradients while sharing as much computation as we can? Okay. So if you're comfortable with everything up until here, you're starting to get an insight into what the backpropagation algorithm could look like. The idea is that we're going to start by computing some error signal and we're going to back propagate, which is to say we're going to move backwards in the graph and propagate that error signal through different intermediate nodes in the graph until we get to the variables that we care about taking the derivative of the loss with respect to. So those could be the weights and the biases of any model. And so in the previous example, we had a really simple use case, which was that of logistic least squares. We can ask what happens when we have a computation graph with a fan out, which means the number of outputs from a given node is greater than 1. And the simple example we can make use of is the regularized logistic least squares model. So this graph is what we had before. That's just the logistic least squares model. And whenever we have regularization, we add in another term. We take our weights and we add in a regularization penalty, which is 1/2 times the square of the weights. So we're pretending everything is scalars here just to make our lives easy as we begin to understand the algorithm. And the existence of this new loss results in this new node being created in the computational graph. And our final loss that we train with is L reg. And that is L plus lambda times R. Okay, so any questions about how we added in 2 new nodes into our computational graph to incorporate the fact that we have regularized, to incorporate the fact that we're learning a regularized model here? All right. And so another example of a computation graph that has a fan out greater than 1 is that of softmax regression. So in softmax regression, we're trying to predict the likelihood that an input x, which in this case is 2-dimensional, belongs to one of 2 different classes, y1 or y2. And so to do that, we would first calculate z1, which is going to be a function of x1, x2, that's going to be dot producted with the vector w with an added bias. We're going to compute z2, which is going to be obtained by multiplying x2 with w21, x1 with w21, x2 with w22, and adding a bias. And then for each of z1 and z2, we're going to apply the softmax operation. And so this set of arrows corresponds to the application of the softmax function, which you'll remember is going to exponentiate each of the values of z, and it's going to normalize it so that we have a probability distribution over these 2 classes. And then at the very end is our loss function that's going to take the targets and apply the softmax cross entropy loss. So I've done nothing here other than take a model that you learned last week and represent it as a computational, and represent the evaluation of the loss function for an input as a computational flow graph. Any questions about what's going on here? Yeah?
Just explain what fan out greater than 1 means.
So fan out greater than 1 just means that there's a node that has multiple different outputs to it. And there's a reason I'm highlighting the fact that these are 2 models with fan out greater than 1, which we'll get to in the next slide. Okay. So the reason I highlighted that is essentially because in order to apply the same error signal rule to these kinds of graphs, we need to make use of the multivariate chain rule. So in the multivariate chain rule, we're going to pretend that we have some functions f of xy, where x and y are functions of t. So I can write down for any given t the evaluation of the function f via this computational flow graph, because as I go from left to right, I evaluate all the intermediate quantities and then end up evaluating f. For this computational flow graph, I can ask, what is the derivative of f with respect to t? Well, the multivariate chain rule tells us that it's df dx times dx dt plus df dy times dy dt. So it's a summation over the gradient of f with respect to x multiplied by how x changes with respect to t, plus the derivative of f with respect to y multiplied by how y changes with respect to t. And again, this should just be review from calculus again, where this is a straightforward application of the multivariate chain rule, although you may not have seen it in the context of what it looks like when you draw it out as a graph. So for this particular example, we're just showing here what happens when you have x is equal to cosine of t, y is equal to t squared, and f is equal to y plus e to the xy. And if you were to apply this formula, df by dx is equal to y times e to the xy. Dx by dt is negative sine of t. Df by dy is 1 plus x e to the xy. So that's the derivative of this with respect to y. And finally, the derivative of y with respect to t is just 2 times t. So that's how you would apply the multivariate chain rule if you were back in calculus class. So how does that inform our understanding of calculating gradients with respect to specific values in the neural network? Well, in the context of back propagation, we have some mathematical expressions that need to get evaluated. We care about sum df with respect to dt. So to calculate df with respect to dt, we're going to pretend that there's some graph that exists before t. We're going to pretend that there's some graph that exists after x and after y. And those two are going to be arbitrary. It does not matter what those graphs actually are. Because what the multivariate chain rule tells us is that if you care about differentiating some function with respect to t, the only thing you need to worry about is how that function influences x and how that function influences y. Because once you have those two key properties, which are this and this, you simply multiply that by how x changes as a function of y and how y changes as a how x changes as a function of t and how y changes as a function of t, and apply the multivariate chain rule in order to get the derivative with respect to t. But we already have a name in error signal notation for that first thing, which is how f changes as a function of x, which is x bar. So we can compactly write down the multivariate chain rule as t bar is equal to x bar times dx dt plus y bar d by dt. I'm going to pause here to see if folks have any questions about what we've covered so far. All we're doing right now is sort of just taking multivariate calculus and mapping it to error signal notation. Okay. So that actually is sufficient for us to describe the entire recipe for how to get gradients with respect to any weights in a computation graph. Because the algorithm for the backpropagation algorithm is as follows. Let V1 to Vn be a topological ordering of the computation graph. And so topological ordering simply means an ordering of nodes such that going from left to right ensures that all the arrows are oriented in one direction. And so for this topological ordering, where parents of each node come before the children, then the forward pass, which is the evaluation of any loss function or any general function in the computation graph, can be simply computed as follows. For each I is equal to 1 to n, you're going to compute Vi as a function of its parents. And by virtue of having done this topological sort at the very beginning, you're guaranteed to always have the computation that you need in the next step be already done in the previous step. So that's how you would evaluate the function. To calculate the gradients or the backward pass, you would back propagate the error signal as follows. You would now reverse and go from n minus I all the way back to 1, and you would write vi bar, which remember is df times dvi, where f is some function that is the result of this computation graph. You would write down vi bar is equal to a summation of the children of vi. So if vi is some node and it has several children, for each child you would need vj bar, and you would multiply that by dvj by dvi as an application of the multivariate chain rule, because you would take the error signals of how f changes the children, you would multiply that with how the children change as a function of the node in consideration, and you would add up all the products across all the children. And so to your question, which is it might be challenging to come up with ways for computers to symbolically manipulate derivatives and functions, this tells us what we need in order to make it work. It tells you that as long as you write a function for which you know what dvj by dvi is, you can always compute gradients. And so whenever you compose functions in this manner, what this algorithm tells you is that just ensuring that you have local gradients available mean that you can use the backpropagation algorithm to compute gradients of any function with respect to any node in that computation graph. And this is an incredibly powerful idea. And it's driven practically all of the advances in machine learning over the last 2 decades. And so when I was when I started out grad school, there was no PyTorch or TensorFlow. There was one library out of the University of Montreal called Theano. And Theano was the first library that allowed you to write down a computation graph. It was the first library that turned this idea into software code, where anytime you wrote a function, it would implicitly create a computation graph, such that you never had to compute gradients anymore. Because you could call .grad, and that would run this algorithm in the back end to compute the gradients of the loss with respect to any input in that graph. And obviously now we have significantly more hardware optimized software platforms like PyTorch, TensorFlow, JAX that can all do this algorithm incredibly quickly. But it's important to realize just how fundamental this idea has been for the development of machine learning. And so now that we know what the actual algorithm is, we can actually run it for the regularized logistic least squares model. So our forward pass, remember, is going to be the evaluation of this particular function, the evaluation of the regularized loss. So we take some input x, we first perform this linear operation, we apply the sigmoid operation and nonlinearity to it, then we evaluate the least squares loss, we evaluate our regularizer for this model, and we add the two up to get the final regularized loss function. Now to take gradients, in order to do learning of this model, we need gradients of this loss with respect to b and w. How do we get that? Well, we can just apply the algorithm that we saw in the previous slide. So this graph is already topologically sorted from left to right. So we're going to go backwards. We're going to ask, what is dl reg with respect to dl reg? And that's just 1. So that's what this term is saying. And to get the gradient of dl reg with respect to dl, well, that's just equal to the gradient of this with respect to dl. So that's just 1. Sorry, that's just, it's 1 because I'm substituting this in here, times dl reg by dl. Similarly, I can ask, what is the gradient of dl reg with respect to dr? And that's equal to dl reg with respect to itself. times dr with respect, sorry, dl reg with respect to dr. And that's equal to lambda, which is the hyperparameter for our regularization coefficient. Now that we have L bar and R bar, we're kind of in business, so we just keep running this operation backwards again. We can use L bar in order to get what Y bar should look like. So Y bar is just L bar times the derivative of how L behaves as a function of Y, so just this local gradient. And the derivative of how L behaves as a function of Y can be obtained via this, which gives us L bar times Y minus T. And then we go backwards again to calculate Z bar. And Z bar is just Y bar times dy dz, which is Y bar times the derivative of the sigmoid operation. And finally, we're ready to compute the gradients with respect to B and W. So B bar and W bar. So W bar, we're going to need to use the multivariate chain rule for, because it has two outputs. So we're going to first need Z bar, and we're going to multiply Z bar by dz by dw. And then we're going to need R bar, and we're going to multiply that by a dr by dw, and we're going to add these two up, because that's the application of the multivariate chain rule, which is what's shown in purple here. That gives us the final answer that we need. And now to calculate the derivative of the loss with respect to B, I don't need to do a lot more because I've already pre-computed what Z bar is. So I can just reuse that computation again and multiply it by dz dB, which is just 1. Now you'll notice something interesting here. The actual calculation of the derivative of Z bar requires you to know what the value of Z was. Because to actually get a number for the gradient, you need to plug in the evaluation of the derivative of the sigmoid operation at the value Z. So which value of Z do you use? You use the value of Z that you got from the forward pass. And so when you think about the backpropagation algorithm, it comprises of these two steps, a forward pass and a backward pass. And the reason why you need these two steps is because the evaluation of the gradients in the backward pass requires you to know the values of intermediate computation in that computational graph that is obtained from the forward pass. And so this is a specific example of how you might be able to do that in the context of a two-class prediction problem now where you have a two-layer model. So in the previous example, we were working with a regularized logistic least squares model. Now we're working with a nonlinear function, a two-layer neural network. And my claim to you is that absolutely nothing is going to change, which is that we're going to use the exact same algorithm to calculate the derivative of the loss function with respect to all of the weights of the neural network. And in this particular case, everything in red here represent the weights and biases of this neural network. So these are the weights in the first layer, and these are the weights in the second layer. So as before, we're going to first do a forward pass that involves computing Zi, so each of Z1 and Z2, as a summation of how X1 and X2 influence Z1. So that's going to be a linear function. Then we're going to compute the sigmoid nonlinearity. Remember, this is a neural network, so there's a nonlinear activation that's applied, and in this case, it's the sigmoid activation that's represented via this edge in this computational graph. And once you have H1 and H2, you have all the things you need to compute the output of the neural network, which is again obtained via a linear operation on the hidden units. And after that, you can apply any loss function you want. In this particular case, it's just minimizing the squared error loss. So it's a neural network that's making a prediction over two regression outputs. So what do we do if we want to take gradients? We do the exact same thing that we did in the last slide, which is first compute L bar. So this is the loss function. We can take derivatives with it with respect to itself. And then we go backwards in the graph. So when we go backwards in the graph, we're looking at this previous equation, yk. Well, in the graph, yk, and let's focus on y1 for a minute, the derivative of y1 is going to depend on L bar times dl dy1, which is exactly this quantity here. And k is indexing into y1 or y2, depending on which one you're looking at. So you would compute both of those. And then you're ready to compute the gradients of the loss function with respect to the weights in the second layer of the neural network. Because remember, the only thing that these nodes depend on is the gradient of the loss with respect to y2. And the only thing that these nodes depend on is the gradient of the loss with respect to y1. So to calculate the gradient of the loss with respect to the weights in the second layer, we just need y bar k. And we can sort of compactly write that down as dl dw. In this particular case, it's dl dwki, 2 representing the second layer, is equal to yk bar, which is the derivative of the loss with respect to yk, times the derivative of yk with respect to wki2. And to figure out what the second term is, we simply need to look at how this equation behaves, and we know that each of the y's is a linear function of the wk's, where the linearity is basically in h. And so that's what's going to form the derivative here. And every time we go further back in this graph, we use the exact same trick where if there's a node that has multiple different fan-outs or multiple different outputs, we end up seeing this summation here corresponding to the application of the multivariate chain rule. And if a node has only a single output, then we would apply the univariate chain rule. Okay. So I'm going to pause here. We'll take a 3-minute break. But if folks have any questions about anything they've seen so far, come by and chat.
In order to get you must calculate the weight and bias.
In order to calculate the derivative of y2 to x2, y2 to x2, h2, you need, wait, so this derivative? This derivative only depends on the derivative of the loss with respect to this number and this number.
I mean, like H2 bar or HI bar. We
Yeah.
need
Oh, yeah, you need,
all the inputs in this layer, like all the weights, the bias, and HI to calculate HI bar.
so hi bar is going to be the derivative, whoops, sorry. Here, we set hi bar is equal to yk bar, which so you just need y1 bar and y2 bar. And that's all you need in order to compute hi bar, because the only other information is how the y's change as a function of the h's, which is given to you by the basically the derivative of the sigmoid operation. Is this? Which is here. So here is the dependence from here to here. is the dependence between how y's behave as a function of the h's.
Yeah.
So the gradient of this function with respect to hi is just going to be w2ki. That's why you see a w2ki here. Yeah.
I was just gonna, I'll come over here. I was just gonna see if my rough intuitive understanding of this makes sense. So basically, like, let's say this is a whatever thing, these are just the layers, and the derivative with respect, like, of L with respect to X is gonna be the composition of all of these. Right?
Yeah.
And then, so what you're gonna do is you're gonna calculate all the values going forwards, and then going backwards when you want to actually, like, change the weight slightly to fix them. Each weight is going to be dependent on, like, the weight at H2 is going to be dependent on all the derivatives here times the actual derivative of the weight with respect to the function.
It's only going to be, so the weight at h2,
Yeah.
the weight that influences h2 is only going to depend on the derivative of the loss with respect to h2.
Yeah.
Everything after that is irrelevant. Once you have that error signal that's propagated all the way back to h2,
Yeah.
that's all you need to compute the derivative. So this is correct.
Yeah, so it's just, you just need these guys,
Yeah.
you reset it, and then, so when you're moving backwards, you're, like, moving, resetting the weights, or, like,
Not
doing the-
quite.
Oh.
So we haven't. So what you're going to do is do the forward pass,
Yeah.
and then you're going to do the full backward pass,
Yeah.
and then you get the gradients with respect to all of the weights simultaneously,
Yeah.
and then you're going to do one reset.
Okay.
You're going to do one update of gradient descent, and then you're going to repeat that process.
Okay, makes sense. But you, like, on each step, you would have the ability to reset the weights there, right? You would at
Correct,
least have
but
that
that is not what
knowledge.
we actually do in
Okay,
practice.
okay, okay.
But you do have the computation to do it if you wanted to, but the problem is you cannot reset it. The reason why is because it means the gradients for it changes the values for the gradients of what the previous layers.
Oh, you need the old values.
You need
to
the old
calculate
values,
the other guys.
exactly.
Okay, cool.
So that's why we wait until we have the gradients for all the weights, make an update, and repeat.
Fair enough, that makes sense. And my last question was what I had asked you, like, initially about the biases and adding multiple biases per layer. It's just like when you say we added the ones, like when we typically did it, not considering neural networks, we just added the ones and we added one bias and we multiplied it by that thing.
Yeah.
If we were to do it this way, I thought it would look like this, where we do
You-
add a bias per thing, but in this it seems to add a bias per, like, node instead of per layer, which is what my confusion was.
I see what you mean. Yeah, I think in this case we just wrote it out explicitly for clarity, but you're right, you just need the one bias because the linear operation over these two, the biases could be combined.
So you could represent this like this too.
Yeah.
With the, oh, okay. Okay.
Like, it's just how we chose to write that down
Okay.
explicitly.
But it is just like one bias per thing. Okay. Okay, makes sense. Thanks.
Okay, we should start. We have quite a bit to cover, so yeah. I'll be around after class if you have more questions. All right. So what we're going to do right now is think about what the extension of this idea looks like in the context of vector notation. So in the previous examples, we looked at how to do the forward pass and how to do the backward pass in scalar notation. So everything was numbers. But we've been spending a lot of time thinking about how to accelerate models with vector computation. And so first you would compute Z as the operation of a matrix multiplication of this vector input plus a bias. Then you would apply the sigmoid nonlinearity here to the vector H to get a vector H. Then you would have your second layer of the neural network, which is W2H plus B2. And your final loss function is going to be a vector norm of the difference between the vector t and the vector output y squared. So the forward pass should all be something that you start becoming familiar with because you've seen it in the context of linear regression and you've seen it in the context of logistic regression now. And all I've done is apply that same vector notation in the forward pass in the context of this two-layer neural network regression problem. So to compute the gradients and train this two-layer neural network, what we're going to do is first calculate L bar, which is going to be 1. And then we're going to apply the chain rule again, but this time over vectors. And so the first one is going to say y bar is equal to L bar times dl dy. which is the gradient of this equation with respect to y, which you can verify is y minus t. And now you'll notice that this is a vector. So the right-hand side of this equation is going to be a vector that is going to have the same dimensions as the forward pass vector. So when our forward pass is scalars, we backpropagate scalars. When we have this forward pass comprising vectors, the error signals that we get are also of the same dimension. And that becomes important when we think about calculating derivatives with respect to W2. Because the derivative with respect to W2 now is going to be, so if we just look at these two nodes in the graph, we know that it's going to be y bar times the derivative of this function with respect to W2, and that's just going to be h. But we need that evaluation to have the same size as matrix W2. So we have the operation that we actually do for W2 bar be y bar times h transpose. So you have a, for example, if this is a 2 by 1 matrix and h is a, let's say a k by 1 dimensional vector, h transpose is a 1 by k dimensional vector, and the result of that is a 2 by k dimensional matrix. And that matrix is a matrix of derivatives of our second weight vector. Now this is in the scenario where the input is a single vector. You can imagine what happens when the input is a batch of vectors, when we're doing batch gradient descent. Well, if it's a batch of vectors, then we might have, for example, an n by d dimensional input that results in a activation y being n by d. And effectively, that ends up in this also becoming a matrix. And then this computation becomes a 2 by n dimensional matrix multiplication with another n by d dimensional matrix multiplication to yield the same 2 by d dimensional matrix that we need in order to calculate the derivative of the loss with respect to W. And so the way that you actually compute this in matrix notation, you have to be careful about making sure that the dimensions align with the inputs that you get in the forward pass, depending on whether you're doing stochastic gradient descent or batch gradient descent. You just need to make sure that the input and output dimensions line up for the variables that you care about taking derivatives with respect to. And again, these are inequalities that you can verify from the matrix cookbook, which I'm hoping most of you have at least taken a look at in the context of deriving gradients. So nothing changes in the context of the actual algorithm itself. The only thing that really changes is just having a little more care with how these are implemented in the back end of most automatic differentiation packages to ensure that the dimensionalities of the matrix multiplications enable you to come up with gradients of your weights, matrices, and bias vectors that are the same dimension that you need them to be. Okay. And so that is basically how you would apply the backpropagation algorithm to take any computation graph and go from the result of evaluation on an input or a batch of inputs to obtaining gradients of the loss function with respect to any parameters in the graph. And you can ask, how costly is this? Well, for every forward pass, you have one add multiply operation per weight corresponding to the linear layer. But for every backward pass, you actually have two add multiply operations. The first one is going to be when you multiply the error signal that's coming from the loss with the local gradient associated with the child node. And the second add is going to come from when you add up the gradients across all the children's for any particular node. So over many, many computations, you find that one backward pass is at least as expensive as about 2 forward passes. And so for a multi-layer perceptron, the cost of this operation of backpropagation is going to be linear in the number of layers, but it's going to be quadratic in the number of units per layer. And so this algorithm allows us to efficiently and, most importantly, exactly compute gradients in neural networks. Because nothing that I've shown you in the last hour is an approximation. We are calculating the exact values of the derivatives using this combination of the forward pass and the backward pass. Gradient descent with gradients computed via backprop is basically the primary workhorse of every neural network that you see today. And when you start learning neural networks, and you'll do some of it in this class, but you'll do most of it in 413, you have to be really careful about how you do this optimization. So there was a question asked in the break. We have enough information to, for example, compute the gradients of the second layer by the time we backpropagate the error signal in this graph, for example, to here. So as we're backpropagating the error signal, at this point, we have everything we need in order to calculate the gradients with respect to W2 and B2. Should we do gradient descent and update those two before going all the way back? And the answer is no, because you want to make sure that when you do gradient descent, you first you propagate the error signal all the way back to the very beginning and to the layers in the very first unit of your neural network. And once you have all the gradients, you make a joint update to them using your learning rate rule. So that's how you learn the weights of a neural network using gradient descent. And typically you'd initialize these randomly. So you'd start out with a random network initialization for these gradients. And even optimization algorithms that are fancier than gradient descent, like second order methods and Newton's method, which you can run on very, very small neural networks, use backprop in order to compute the gradients. And so despite its success, backprop is pretty much widely thought to be neurally implausible. And what that means is that people don't think that it is the way by which human neurons actually update their own weights. But it's nonetheless an incredibly practical and successful learning tool for neural networks today. And so really this algorithm is the backbone of auto differentiation, which means that if we construct our network out of primitive operations like adds and multiplies, and frankly, as long as we can write down the derivative of the output with respect to the input, which is the only piece that we need, then we're guaranteed to be able to compute derivatives exactly throughout any neural network that is a composition of such functions. And that's a really powerful idea that's enabled us to innovate so dramatically to create things like ChatGPT. Because the difference between an MLP and the model underlying ChatGPT is in the neural architecture. It's in the function that maps from input vectors to output vectors, and the composition of those functions. And the main reason over the last decade we've been able to innovate in those neural architectures is because we didn't have to worry about the learning algorithm. We never had to derive it by hand for each new neural network architecture that we came up with. We could just come up with the function that we wanted to experiment with and then run autodiff, and it would give us gradients. And we'd be pretty much guaranteed that those were correct, and we could learn with them via gradient descent. And so that's driven a lot of the experimentation practice and enabled us to get to where we are right now. So there's lots of libraries like PyTorch, TensorFlow, JAX, and although these libraries automate the backward pass for you, it's really important that you know how they work under the hood, which is what these lecture slides actually teach you. Okay, so that brings us to maybe thinking about different kinds of neural networks, and we'll talk about one kind of neural network in the second part of this class today, and those are convolutional neural networks. So often in machine learning, we try to design neural networks that are going to be robust to certain properties that we'd like. So for example, if I'm looking at a picture of you, and if I move from, say, left or right, then it doesn't change my perception about things like the number of students in the classroom, the color of the chairs, the number of projectors in the classroom, and so on. So we'd like a neural network to also be robust to transformations of their input, like translational shifts. We don't want the robot to say there's one cat, and then if I move the image a little, the neural network says there's 50 cats. That doesn't make sense. And so people have started thinking, and this is back in the 70s and the 80s, started thinking of ways to create neural networks that satisfied certain properties. And one of them is this idea of invariance to particular transformation, which is that the image, if transformed slightly, should not change the output of the neural network. So how do we think about that in the context of an image? So before we come up with a particular design principle for that idea, we need to think about what it actually takes to learn a neural network of an image. Let's say you have a 200 by 200 pixel RGB input image. If you have 1,000 dimensional hidden units, then you effectively have an input size of 200 by 200 by 3, which is about 120,000, because I'm taking the R, the G, and the B plane of my image, and I'm turning them all into this one giant vector by flattening those three matrices, and that one giant vector has 120,000 dimensions. And then, if you're telling me that I have to learn a linear operation of all of the inputs to all of the hidden units, that means I need 120 million parameters in just the first layer of my neural network. So that is a lot of parameters. And in many, many cases, and perhaps we might be able to get away with learning something like this now, but 20, 30 years ago, before we had GPUs that were that big, there was no way this was feasible. So people had to be clever about what we wanted to learn and how to create neural networks that, for example, were a little more efficient. And so the intuition behind convolutional neural networks is to think of the idea that when we're looking at an image, what we want to do is identify shared structure. If I'm looking at this image of this classroom, I know that there's a lot of chairs in it, and I want to be able to detect that there's a chair in it. To detect that something has a chair, maybe I need a right angle detector, because I can count the number of right angles there are, see how close they are together, to inform my understanding of whether there's a chair in front of me. So let's say I care about coming up with this edge detector, corner detector, or this right angle detector. What I want this detector to do is not just work on one part of an image. I would like it to work on all parts of the image, because the concept that I want to extract is identical across all parts of the image. The meaning of a right angle doesn't change if I'm looking at the top left of the image or the bottom right of the image. So I'd like that to be a single concept that I extract. And one way to do that is by using shared structures. And so we want feature detectors that are going to be applicable in multiple locations of the image. What does that look like for a fully connected layer? Well, for a fully connected layer, we have 120 million parameters, which means for the top left of the image, I have a dedicated set of parameters that are looking at the top left of the image, and another dedicated set that are going to be looking at the bottom right of the image. Because in a fully connected layer in a neural network, there is one connection from every input to every hidden unit. The problem here is that we want to think of coming up with structures or neural networks that are locally connected. So we don't care about looking at everything in this entire image at once. We want to first decompose the problem of image understanding into finding, for example, right angles. And to find a right angle in the top left corner, it suffices for me to perform some local computation in the right corner or the left corner or vice versa. And so we want to have these convolutional layers that represent a set of hidden units that only characterize or look at a small region of the input at a time. And the other property we'd like to have is to share the weights of that operation, which is to say that if I was looking for an object here, and if I was looking for the same object here, I would like the computation for how I compute the output as a function of that input to be shared. So I want to tie the weights of the feature output at this area of the image to be the same as this area of the image. So each set of hidden units is going to look at a small region of the image, and the weights are going to be shared across all of the image locations. So these are just two properties that I might want to have if I want to decompose this task of moving away from 120 million parameters to being able to learn localized features that are much more representative and are present across multiple regions in the image. And if I have such an operator, and I haven't told you how we get that, I might want to stack it just as we would with a multi-layer perceptron. So let's say we had this convolutional layer that, for example, is going to look at small regions of the input and come up with a decision on whether or not a feature is present. And it's going to be the exact operator that's going to be applied at different parts of the image. Then I can repeat that operation multiple times to learn a stacked convolutional neural network. So how do I take this idea of having a small set of weights, a small set of functions that are going to be repeatedly applied across an input? How do I operationalize that idea? So the way that's done in one way that's done in machine learning is to leverage the idea of convolutions. So how many of you have heard the term convolutions before in any other context? So a few people, if you've taken any classes in signals and systems or electrical engineering, the idea of convolutions is a very classical idea. And it shows up a lot in engineering. But in the context of machine learning, we use the convolution operator as a means for us to operationalize this idea of taking a set of weights and scanning it across the entire input image. So let's see why that's true. So we'll start off by thinking about the 1D case, and then we'll move to the 2-dimensional case. In the 1-dimensional case, we'll say X is an input signal, which in 1D is a waveform, and W is a set of K weights. So we have some signal, X, and we have some set of weights, W. And our goal is to compute the convolution operation of X convolved with W. And so the Tth value in the convolution is mathematically defined as a summation of 0 to k minus 1 of X of t minus tau times W of tau. And if you haven't seen this before, this is kind of a complex equation to take a look at and immediately get an intuition for what it's doing mathematically. So what we're going to do is look at two different ways to compute the result of a one-dimensional convolution. So the first way is to use elements of X to scale the positioned or translated copies of W. So let's look at what that means. So X is going to be this vector 2, minus 1, 1, and W is going to be the vector 1, 1, 2. I'm going to use elements of X, so 2, minus 1, 1, and that's 2, minus 1, 1, to scale, and that means to multiply, positioned or translated copies of W. So that means I'm going to take W, I'm going to copy it and put it in the position that of the element of X that I'm scaling W by. So the first element of X that I'm scaling W by lies in the first position. So I'm going to put it here. So remember, 2 shows up here. So I'm going to center my weight matrix here and then multiply all of these numbers by 2, which gives me 2, 2, 4. Next, I'm going to take my filter W and center it at the location of -1, which is going to be in the center of this x-axis. And that gives me -1, -1, -2. And then I'm going to take my weight matrix again, my filter W, and then I'm going to center it in the position corresponding to where 1 is in X, which is going to be the third position. And that gives me 1, 1, 2. And then I'm just going to add these numbers up. So that gives me 1 plus, that gives me 2 plus 2 minus 1, 1 plus 4 minus 1 and 2. The second way to compute the convolution, and this one is a little bit more intuitive, I find, and it actually corresponds to the idea that we were talking about before, which is to take a set of weights and scan through an input, is the flip and filter method. So the flip and filter method says I'm going to take W and I'm going to flip it, which means to reverse it if it's a list. So I'm going to have 2, 1, 1 be the W that I have. So I'm going to take 2, 1, 1 and go from left to right over my input image X. So this is my input image X. And I'm going to scan from left to right. And each time I'm going to advance by 1. And this, remember, is in, it's in discrete time. So each of these correspond to indices of X. And every time there's an overlap between X and W, I'm going to compute the product of everything that shows up, everything that's overlapped. So there's no overlap here, so that's going to be a 0. There's no overlap here, that's going to be a 0. There is an overlap here, and that's just going to be a 2. And that ends up with this first 2 here. After some time, I'm going to move it by 1. So there's no overlap here, so that's going to be a 0. There is an overlap here, that's going to be a 2. And there is an overlap here, that's going to be a -1, and that results in 2 minus 1, which is 1. So intuitively what we're doing here is that we're taking our vector W, we're flipping it, and then we're scanning from left to right across this input signal. And the output of this operation is the result of an element-wise dot product whenever there is an overlap, followed by a summation operation. So if we think of this operation of element-wise multiplication and then summation as the identification of the existence of some quantity of interest that is identifiable by this W, then what we're doing is we're checking the entire signal for how many times W shows up, the pattern embedded inside the numbers of W. And again, this is going to be a little bit of a vague idea until we see concrete examples of what a convolutional kernel actually is. But hopefully the flip and filter method gives you an intuition for why this operation enables you to take this small set of weights and scan through the entire input image in order to compute an output where each number in the output represents the likelihood or some semblance of the probability of what W represents in the input. And so the convolution operation satisfies commutativity and linearity. And the more interesting case happens in the case of 2D convolutions, which is why we really... So if you're doing machine learning and you work with signals, so if you work with sound waveforms or if you work with spectrograms, 1D convolutions are used frequently in the analysis of those signals. So lots of people use 1D convolutions to build neural networks of speech models. But if you're working with images, you need 2D convolutions because you want to have this operator, this filter, operate over both the height and the width dimension of this input image. And so the mathematical definition is analogous, and so we're going to apply the same sort of two methods that I identified to you in the 1D case, but now in the 2D case. So here what we're going to do is we're going to use elements of W to rescale positioned copies of X. So X and W are commutative, which is why we're able to do that. But we can ask, we're going to take elements of W this time. So 1, 2 and minus 1. And for each element of W that we're going to scale x by, we're going to put x in the position where that element is in W. So element 1 is in the top left position of W. So we're going to take our matrix X and put it in the top left position of this 4x4 matrix. Similarly, element 2 is in the top right position. So we're going to take our input X and put it in the top right position of this 4x4 matrix. Similarly, minus 0 is going to be irrelevant because that's going to be all zeros, and minus 1 is in the bottom right position, which is where we'll put element X. And after we rescale all these numbers, so this becomes a 1, this stays a 3, this becomes a 2, this becomes a 6, this becomes a 2, we'll simply add up all of the numbers across these 4x4 matrices to get the final output of our convolution operation. And I'm going to show it to you for what this number looks like, because here we're going to add 0, minus 1, and that's going to be a minus 2. So, as I said before, like in the 1D case, yeah?
How do we know it's going to end in a 4x4 matrix?
So this is a really good question. In this particular case, you set this up so that there exists overlap between the two signals that you're convolving. And I'll tell you why it's a 4x4 matrix. It's a little easier to see in the case of the flip and filter method. Because in the flip and filter method, you take your W, your filter weights, and then you flip them along the diagonal. This is not a transpose operation. You're going to flip this matrix W along the diagonal. So you're going to get minus 1, 1, 0, and 2, which is the same thing here. And you're going to scan W across this entire image. And now you can ask, well, how do you know what the output size is? If you're scanning W across the entire image, the edge cases are going to happen when there's at least the least intersection that you need, but when you do that scanning operation is over one element of both matrices, which happens when W is here and X is here. And so in this particular case, it ends up being 1 times 1, which is equal to 1. And everything else is a 0. So you assume that X is going to be 0 padded along both its height and width in both directions, and you're scanning this matrix from left to right and from top to bottom. But really the only output you will see is when there exists some overlap between W and X. And that dictates in some degree the increase in dimensionality that you'll observe with the convolution operation. And so if your flipped W overlapped with this portion of your input X, you would multiply 3 times minus 1, minus 1 times 2, plus 1, which gives you minus 4. And so, again, the operation that you're doing is the same. You're taking a dot product of all the elements that overlap, an element-wise dot product, and then summing them up in order to get the number in the output. So to go back to the intuition that we wanted, like this operation of convolution, when you think about it from the flip and filter perspective, what it's doing is it's taking a matrix or a vector W and it's scanning it throughout the entire input signal. So if your W represents the probability of identifying a right angle in this image, and if this was the input image, then this might tell you the probability of there being a right angle in the top left portion of the image. This might tell you the probability of a right angle in the top right portion of the image, and so on. Yeah? So flipping W is mostly to stay consistent with the mathematical notation of what the convolution operation is doing. In practice, what we're going to do is learn W anyway. So it sort of doesn't matter whether we flip it or not, because those weights are going to get learned via gradient descent rather than it being a fixed filter. But to stay mathematically consistent with the convolution operation, we're just writing it out as the flip and then scan operation. And if you don't flip it, you won't get the same as what you saw in the previous slide, and you can verify that. Yeah?
In the previous
if the other component of W was a 0 here. Oh, you mean this one? If, yeah, you would have 4 if this was like a 3. If this was a 3, you would have 4 computations to do. Yeah.
Sorry, I might have missed it, but the purpose of involvement is motivated to reduce the amount of difficulty, right?
Right.
But in this case, we're set now.
Yeah, so that's a really good point, and we'll get to what we do as a consequence of that. But before we get to answering that specific question, it's important to understand what this convolution is doing. Because like I said, this is not a new idea, and people have been taking filters in computer graphics and vision and convolving them with images for a long time before neural networks came along. So if you had this particular filter, this is what's called a blur filter. So if you take this image of Jeff Hinton, and then you apply this convolution operation of this filter through it, and you'll notice that it's a symmetric kernel matrix, so it doesn't really matter if you flip it. But what that means is scanning this image of Jeff, and at each point in time, taking this matrix and then applying the dot product of the overlapping elements and summing them up and looking at the output. So this is the output of X convolved with this matrix W. You would get this output image. And qualitatively, this is blurring the original image that you had. It turns out, if you just turn the 1s to -1s, you can reverse the operation of this convolution, and this is a sharpening kernel. And if you have and add in a bunch of zeros along one of the columns of this kernel matrix, it removes all of the content in between the lines and preserves just the edges. So what I want to communicate here is that by changing around the numbers in these kernel matrices, you can do some really interesting things to your input image. And that should give you an intuition for the fact that it's a worthwhile endeavor to think about how we can learn these kernels from data to solve predictive tasks at hand. Because if we can learn that we have a prediction task that's responsible for counting the number of edges in an image, then maybe learning this kernel is the right thing to do to solve that problem. But we want to let the data be able to decide that. And that's what convolutional neural networks give us the ability to do. So there's two types of layers. There's convolutional layers called detection layers, and then there's pooling layers. And the convolutional layer has a set of filters, each of which is going to produce a feature map. So in practice, what you do is you take an input image, and then you have k different kernel matrices. You don't just convolve it with one kernel, you convolve it with k different kernels. And the result of taking your input image and convolving it with k different kernel results in k different feature maps. And it turns out that if you were to visualize the first layer filters in a convolutional neural network, you'll see that a lot of, so this is a, each of these corresponds to the visualization of one of those kernel matrices that was learned in a convolutional neural network trained on image classification tasks. So you see here that it's mostly trying to identify edges in the first layer of a convolutional neural network. And if you go higher and higher in the convolutional neural network, and this paper is a nice one to read if you're interested in looking at that. It's about a decade old, but I think the results still hold. You'll find that the features learned are more compositional in nature. But back to your question. So before we get back to your question of how do you actually reduce the dimensionality down from the feature maps, because convolutions can increase the dimension, we also need to learn about nonlinearities. Because it turns out that convolutions are linear operators. And this might not at all seem obvious to you, but there's a class of matrices called, they're basically these tri-diagonal matrices that you can write down, and if you were to take your input, vectorize it, multiply it with a matrix, and then interpret it back as an image again, it would look at, it would be exactly the same as applying a convolutional operation to it. That matrix basically has multiple different copies of this kernel embedded in it in very specific locations to mimic the fact that it's performing a convolution operation. But at the end of the day, the convolution operation is therefore a linear operation. over a very, very sparse matrix. And what you need to make sure that you learn a compositional nonlinear neural network are nonlinearities. So what people do is they first apply a convolutional layer, and for each of the feature maps, they apply a nonlinearity, like the rectified nonlinearity. And so this is just showing you what happens when you take two feature maps and apply a linear rectification to it. So this one might be more sensitive to horizontal edges versus this one being more sensitive to vertical edges. And finally, as your colleague mentioned, in the 2D examples we saw, the size of the result of the convolution operation was larger, which is to say we increase the dimensionality of the input by applying the convolution operation. So doesn't that mean our images get bigger and bigger? And the answer is yes. And so what people do when that happens is an operation called max pooling. So when they get an output feature map, rather than look at all of the features in that feature map, they take a max operation over subsets of it. So in this particular example, if you had 7 output features in your feature map, then you might take the max over the first 3, the max over 3, 4, 5, and the max over 5, 6, 7. And that gives you a new set of features that is dimension 3. So that's almost a 50% reduction in dimensionality via the operation of max pooling. And you don't have to do a max, you can do an average or any other kind of operation, but max and average are two of the most popular choices of operations people use for the pooling layers. Yeah?
So like in the diagram, some nodes like Z3 and Z5 go to multiple different
Yeah.
ways and some only go to one. Would we choose like which ones to weight more like that or no?
Yeah, so you could choose the degree of overlap in how those features contribute to the output of the pooling operation by changing what's called the stride of the pooling, which is not something we'll cover. But you can sort of think of the pooling operation also like a filter that kind of scans from left to right, or like left to right and top to bottom. And instead of doing a dot product with a matrix, it just applies the max operation over those units of that image. And in practice, that's often how it's implemented. And so a convolutional neural network has the following 3 steps. You first apply the convolutional layer, you then apply the a nonlinearity, and then apply a pooling layer to it. And then you might stack multiple different convolutional neural networks on top of each other, because each of these feature maps can be interpreted as an image for the subsequent convolutional layers to operate on. And it turns out that because you end up doing operations like max pooling, the higher layer filters can effectively cover a larger region of the input than equally sized filters in the lower layer. What that's saying is that the sensitivity of a particular feature, a particular hidden unit in a higher layer after max pooling is going to span a much wider region of the input image. Because the pooling operation, because remember, each of these feature maps in the first convolutional step might only cover a local region of the original image. So this is going to be, this region is going to be represented here, this region is going to be represented here, and this region is going to be represented here. But now if you were to take all of these and pool over them to get your final output of the max pooling operation, then the max pooling operation effectively spans a larger input space in terms of being sensitive to it. So this is in some sense how you get higher and more compositional features being learnt in the kernel matrices of higher layers of convolutional neural networks. And so at this stage, we can go back and ask, did we achieve what we set out to? Well, there's 2 concepts here in terms of a function. You can have a function that is equivariant, which says that if you translate the inputs, the outputs are going to be translated by the same amount. Or you can have a function that is invariant, which says if you translate the input, the prediction of the function is not going to change at all. And so pooling layers provide a degree of invariance to small translations of the image, while convolutional layers provide a degree of equivariance to the image. And so the combination of convolution and pooling layers enables us to get a degree of robustness to spatial transformations, which is to say, if I were to move things around, the feature maps that are computed as the output of a convolution operation would also move around, but it would only move around a little bit because it's going to be limited by the pooling operation. And so each unit is connected to each unit within its receptor field in the previous layers, and this includes all of the previous layers' feature maps. And so if your input is actually a grayscale image like MNIST, then you only have one input image, so to speak. But if you have a color image, you have 3 channels. And these you can sort of think of as 3 feature maps that you're going to provide as input. And each of those feature maps is going to be convolved with k different kernels in the first layer. So you get k times 3 output feature maps in the second layer, and you keep going after that. So you apply a max pooling, and then you apply a few more filters, and so on. And so one of the first convolutional neural networks was designed in 1998, and it was deployed in order to read letters and understand digits that were digits and actual characters that were written out in letters. And the convolution operation worked on a 32 by 32 image patch of the actual input. And so it would take these feature maps and go all the way until it predicted 10 outputs all the way up until 9. This is in the case of MNIST, so the letter A is not going to be predicted there. But more interestingly, the actual neural network that won the ImageNet competition in 2012 was a very, very deep convolutional neural network. So remember, one of the things we said was that a lot of the progress in machine learning was triggered by the wave of advances following the AlexNet model. And the AlexNet model is essentially a version of the LeNet model, but scaled up. It's much bigger, deeper. And this ResNet model was the one that ended up winning the ImageNet competition in 2012. And so since then, so in 2012, the error rate was about 16.4%. And like 3 years later, with the advances in residual neural networks, it ended up dropping down to about 4.5%. And human level performance is about 5%. So even in 2016, 15, we have almost near perfect level human recognition, on at least on the ImageNet competition benchmark data set. And so the competition itself is no longer running because the performance is already quite good and it's surpassed human level performance, but the benchmark is still used academically to see how well new algorithms behave, new learning methods behave, and new optimization strategies behave. So if you read machine learning and deep learning papers, a lot of them will use the ImageNet benchmark in order to get an assessment of how well any method does relative to the current state of the art. Okay, so that sort of concludes everything you'll need to know for the actual midterm itself. I'm going to give you, we have a few minutes left, so I'll stick around for questions. But if you have any more, please come by and ask, and good luck studying. So the midterm office hours should also be posted as well.